Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the last lecture we studied FRF measurement with a shaker using random excitation. In this lecture we are going to look at FRF measurement with a shaker using some other excitation signals. So we are going to look at some variants of random excitation signal and also sine excitation signals. So in this lecture also we are going to simulate the process of FRF measurement on a cantilever structure, and the idea is to understand the various steps which are involved in the process of FRF measurement using other excitation signals. So we are going to use the same test setup as we used in the previous lecture for measurement with random excitation, right. So we have 5 test points, right, as shown in the figure, and then we have we are going to conduct a roving accelerometer test with shaker fixed at test point 5, and then we are going to measure translational FRFs in the vertical direction, right, at these 5 test points. And we would use the same time and frequency domain parameters as we use for the FRF measurement with random excitation. So we are going to use a frequency range of 0 to 400 hertz, right, and then number of samples 4096, right, number of samples in the time domain, and the other parameters would get automatically fixed, and which are as follows. So we have a sampling frequency of 1024 hertz, anti-aliasing filter cutoff frequency 512 hertz, a record length of 4 seconds, frequency resolution of 0.25 hertz, right, and there are 1600 lines in the spectrum of the signal. So now let us look at what are different variants of random excitation signal that have been developed. So we saw in the previous lecture that the random signal, it suffers from leakage in the frequency domain, because any finite length of the random signal will not be periodic, right, it will not satisfy the periodicity assumption, and hence there would be leakage, and then that necessitates the use of a window function, right, and window function though helps reducing the leakage, but it also distorts the signal in some way, right. So artificially we are changing the signal, that is something if possible should be avoided. So that is why some variants of random excitation signal have been developed in order to address the limitations of random excitation signal, and these variants are pseudo random excitation, periodic random excitation, and burst random excitation. Okay. So these are the 3 excitation signals, variants of random excitation signal we are going to study. So we will look at one by one these signals and look at the process of FRF measurement using these signals. So let us first of all look at what is pseudo random excitation. So pseudo random excitation is basically a signal that is generated by periodically repeating a block of length t of a random signal. So what we do, we generate a random signal of length t, and then we repeat this length t, right, to obtain the excitation signal. So the excitation signal obtained in this manner is nothing but pseudo random excitation signal. Okay. And what is the advantage of this? The advantage is that if we take now a record of length t from this signal, or an integer multiple of length t, right, if we take, then that signal or that length of signal would be periodic, it would satisfy the periodicity assumption, and therefore it would be free of leakage if a DFT of the signal is taken. So therefore no window function would be required, because no leakage is expected in the signal, right. So in this way then it addresses the limitation of the random excitation signal, right. So it eliminates the use of any window function. So how this pseudo random excitation signal is generated? So this is synthesized using discrete harmonic frequency components in the frequency range of measurement. So for the present case we have f max as 400 hertz, right, and then we have a frequency resolution delta f of 0.25 hertz. So we have 1600 number of frequency lines, right, in the spectrum. Now as there are 1600 frequency lines in the spectrum, what we need is a random signal, which has roughly uniform magnitude, right, over this band of frequency. Therefore, to realize such a signal, what we do, now we add all the harmonic components corresponding to these 1600 lines, and the amplitude of these harmonic components is taken constant for all of them, but the phase of these harmonic components is taken as random, right, and then all these 1600 harmonic components we then combine. The signal that is resulted is nothing but a pseudo random excitation signal, right. So, it will be a random signal and it will be pseudo random excitation signal. Now, this is called pseudo random signal because it is not truly random, right, because we are using discrete harmonic components to generate the signal, but at the same time it has the characteristics that its energy is uniformly distributed throughout the band of frequency. So, in that sense it is random, and that is why it is referred as a pseudo random signal, not a truly random signal, but almost like a random signal. Let us now synthesize a pseudo random voltage signal. So, the figure shows the pseudo random voltage signal synthesized over a length of 4 seconds, right. So, we can see the signal varies in a random manner over this 4 second length, but the important point is that this would be periodic, right. If we repeat this signal from, let us say, 4 to 8 seconds and 8 to 12 seconds, it will constitute a periodic signal. And then the excitation which results over this 12-second length is also shown on the right, right. So, we see that the excitation also varies in a random manner. Now, the important thing here is that we should take the measurement of force and excitation only when the steady state conditions have reached. Okay. So, when the force is applied, when the excitation is applied on the structure, there will be some initial transient, and then because the signal is periodic, the structure would reach to a steady state after some initial transient phase. So, we must take the measurement of force and excitation when this steady state has reached. Okay. So, therefore, we should wait for some initial time, and once the transient has decayed, then we must take the measurement. So, in order to see whether there really exists a transient or not, what we do here in this case is that we subtract the last block of response data, right, from all 3 blocks. So, let us look at the result of this subtraction. So, we note from this plot that there is some transient response at the beginning, and after the first block of data of 4 seconds, there is no transient response left. Therefore, after first 4 seconds, we can take the measurement of force and excitation on the structure. So, now we perform spectrum averaging, and that gives us the FRF estimate. So, let us look at the point inertance and coherence obtained in this manner. So, we see that coherence is very good, right, except at frequency close to 0, the coherence is very good throughout the frequency range, and the FRF estimate also is very good. So, are there any disadvantages of pseudo random excitation? So, we see that pseudo random excitation has one disadvantage, that if there are any nonlinearities which are there, then it does not yield an FRF corresponding to a linear approximation of the structure. Okay. So, if there are any nonlinearities, then the pseudo random excitation would not yield a linear approximation of the structure. If there are no nonlinearities, then there is no issue, but if there are any nonlinearities present, then our intention would be to obtain an FRF estimate which corresponds to a linear approximation of the structure, but pseudo random excitation would not be able to yield such an estimate, and that is because we are using the same synthesized signal, right, over various averages. So, the amplitude of the force remains constant over all the averages. There is no variation of the force amplitude over a broader range, and therefore, the nonlinear response is not excited, and that is why the averaging of nonlinear response would not occur, and we would not get a linearized estimate of the FRF. The FRF estimate that would result would correspond to the force amplitude that has been used for excitation. Okay. So, therefore, if the intention is to obtain a linearized estimate, that is something cannot be obtained using pseudo random excitation signal. So, in order to address this shortcoming of the pseudo random excitation signal, periodic random excitation has been developed. So, what is periodic random excitation? So, the periodic random excitation uses the synthesized signals which are generated using a random amplitude over the averages. So, what we do, we change the amplitude of the force, right, while generating the excitation signal, okay, from average to average. So, therefore, a different force amplitude is used for every average, and therefore, the periodic random excitation signal excites the structure with a broader range of force amplitudes, and therefore, any nonlinearities, if they are present, then nonlinear response would be averaged out, right, and then it would result into a force estimate which corresponds to a linear approximation of the structure. So, therefore, by using different force amplitudes over different averages, the periodic excitation, periodic random excitation tries to generate a response over a broader range of amplitudes, thereby the averaging of the nonlinear response to be accomplished. Also, the added advantage is that since the signal is still periodic, so the excitation signal over one average would satisfy the periodicity assumption, okay, and therefore, the signal would be leakage free, and hence the window is not required, right, for measurement. So, let us look at now for average 1, what is the force applied on the structure and what is the excitation at the test point phi. So, you can see this is the force on the structure and the resulting acceleration, and the 3 blocks of data are shown, okay. And now we, for the average 2, for the next average, we do not use the same force amplitude. So, we generate a signal of length 4 seconds again with a different force amplitude and different phase angles, right. So, this is the force and the resulting acceleration during average 2. So, now we see that the force amplitude is different. So, it is now a different random excitation signal, but for each average the excitation is periodic and they satisfy the periodicity assumption, and thus eliminating the leakage and any need of any window function. Let us look at another variant of random excitation called burst random excitation. So, is there any disadvantage associated with pseudo and periodic random excitation? The pseudo and periodic random excitations are periodic, right, hence the energy is distributed over discrete frequency components, okay, and is a disadvantage compared to pure random excitation. We saw that the pseudo and periodic random excitation signals, they are synthesized by combining the discrete harmonic frequency components over the frequency range of measurements. So, they do not contain energy which is distributed continuously over the whole frequency range of measurement. It is concentrated at discrete frequencies, but a pure random excitation signal excites the structure continuously over the whole frequency range of measurement, not at only discrete frequencies, okay. So, in order to address this shortcoming, the burst random excitation signal has been developed. So, the burst random excitation essentially consists of a random signal making up only a portion of the record length t with no input in the remaining part of the record length. So, therefore, in the burst excitation signal, the random excitation exists only over a portion of the record length t, right, and in the remaining length of the record there is no excitation. Let us look at the force acting on the structure and resulting excitation when a burst random excitation signal is used. So, you can see we see on the left hand side the force versus time history. We see that the force is non-zero over a certain portion of the record length and then it becomes 0. So, this is how the burst excitation signal is generated, and this is how the force is applied on the structure. So, what is the effect on response? So, we see that excitation is random over the length over which the force is non-zero, right. The burst excitation is there over that length, the response is also random. But once the force becomes 0, the response also gradually decays. So, this burst excitation signal is designed in such a manner that the response after the force becomes 0 decays completely within the record length. So, that is one important consideration in designing a burst random excitation signal. We would like that once the burst part of the excitation is covered, then the response should decay within the record length. So, that would ensure that there would be no leakage when the DFT is taken and the use of window is completely avoided. So, let us look at the point inertance which is measured in this manner and the corresponding coherence function. So, we see that coherence is good except at the resonance and anti-resonance frequencies where it has dropped, right, but otherwise the coherence is good and the FRF estimate is also good. So, this burst random excitation signal also requires a good number of averages, okay, in order to obtain a good estimate of the FRF. So, what are the advantages of burst random excitation? So, the first advantage is that there is no leakage and no window is required, right. So, use of window is completely eliminated. Then for each average, the burst part of the excitation signal is different, okay. For each average, the burst part is generated independently, and hence this excitation allows obtaining a linearized estimate of the FRF in case the structure has non-linearities. Therefore, the range of force amplitudes which is used for excitation is broad, right, because first of all the random signal is used to generate the burst, and over the averages also the burst is different. So, a broad range of force amplitude gets used to excite the structure, which results into a broad range of amplitudes of the response, and any nonlinear response if is generated, then that gets averaged out, resulting into a linearized estimate of the FRF. Another advantage is that the energy is distributed continuously over the measurement frequency range, unlike the pseudo and periodic random excitations which have energy concentrated at discrete frequencies. So, basically it combines the advantages of random, pseudo random and periodic random excitation signals, right. So, burst random excitation combines the advantages of all these three excitations. But burst random excitation requires a number of averages to get a good quality FRF. So, therefore, now in this way we looked at three variants of the random excitation signal, right, the pseudo random excitation, periodic random excitation and burst random excitation. Now, we look at another kind of excitation signal which is based on use of sinusoidal force, right, which is called as sine excitation. Sine excitation uses excitation force at a certain frequency, okay. So, we are going to now look at two kinds of sine excitation. One is what is called as step sine, and other is what is called as sine sweep or sine chirp, right. Let us look at these two. So, let us look at what is step sine. So, step sine involves excitation using a sinusoidal force of the desired frequency. So, we take the measurement at one frequency, right, means let us say we want to take measurement from let us say 100 hertz to let us say 400 hertz, let us suppose. So, we use a harmonic voltage signal of 100 hertz, we excite the structure, right, with that voltage signal, and then we take the measurements at that frequency when the steady state has reached, right, and therefore that gives us the estimate at frequency 100 hertz. And now we step up the frequency to the next frequency. Let us say if we are using a frequency resolution of let us say 0.5 hertz, then our next frequency would be 100.5 hertz, right, and then we repeat this process and then we get the FRF estimate at 100.5 hertz. So, in this way we step up the frequency and in sequence take the measurements at each discrete frequency, and then we cover the whole frequency range in this manner, right. So, the advantage of this strategy is that the leakage can be eliminated, right, and the windowing can be avoided, because when we are exciting at a particular frequency, we know the time period of the excitation signal, and then we can choose the record length according to this time period, right, by taking the record length to be integer multiple of this time period of the signal, and that ensures that there is no leakage and the windowing is completely avoided. So, that is the advantage. Another advantage of sine excitation is that if we want to study the nonlinearities in the system, right, we want to detect the presence of nonlinearities and we want to quantify the nonlinearities, then sine excitation signal is very good, because we can very closely control the amplitude of the force, right, at each frequency, and then by changing the amplitude of the force we can study the effect of force amplitude on the response and thereby try to detect the presence of any nonlinearities that might be there, right. So, that is why sine excitation is a preferred signal if the objective is to study the or to detect the presence of nonlinearities or to quantify the nonlinearities in the system. However, with sine excitation we take the FRF one by one at discrete frequencies. So, therefore, it requires a very long time for the measurement, right. It does not allow measurement of FRF over the whole frequency range in one go. In the random excitation, the whole frequency range of interest was excited in one go, right, and the FRF which is resulted is over the whole frequency range of measurement. But in sine excitation, we are obtaining the FRF magnitude and phase at discrete frequencies, right, and then we need to scan the whole frequency range in order to obtain the FRF estimate over the full frequency range of measurement. So, the test requires a long time. Also, we should note that if we are interested to find a linearized estimate of the FRF, we want to find FRF corresponding to a linear approximation of the structure, then step sign will not be able to yield that estimate, because it excites the structure with a certain force amplitude, right, and therefore the linearized estimate cannot be obtained. Let us now look at another sine excitation signal called sine chirp, right. So, sine chirp basically is a sine sweep signal, where the frequency of the signal is continuously swept from a lower limit of the frequency range to the higher limit of the frequency range. Therefore, the limitation of the step sign excitation, which requires a long test time, is addressed in the sine chirp signal by sweeping the frequency continuously from lower limit to higher limit. Therefore, with one excitation signal itself, the whole frequency range can be excited. There are two ways in which the frequency is generally swept. One is the linear sweep and another is the exponential sweep. So, in the linear sweep, the instantaneous frequency of the signal is changed linearly with time, right. Therefore, the sweep rate, which is the time rate of change of frequency, is constant. So, in the linear sweep, the frequency is changed linearly from lower limit to the higher limit, and therefore, the sweep rate is constant, that is the rate of change of frequency as a function of time is constant. In the exponential sweep, the sweep rate is varies exponentially with time. Let us look at the linear sweep. So, now we are going to generate a sweep signal with the frequency swept from 100 to 300 hertz in 1 second, right, and then we will also see the DFT magnitude, right, the magnitude of the frequency spectrum of this sweep signal, to get an idea that what kind of frequency content is present in a sweep signal. So, on the left hand side we see a voltage signal, right, swept from 100 to 300 hertz in 1 second, okay, and this signal has been shown on a log time axis. And so, we see that the frequency of the signal is low in the initially, and then it continuously increases and it reaches to 300 hertz at the end of 1 second. On the right hand side we are showing the magnitude of the DFT in dB, and we see that the magnitude of the DFB is predominant over the frequency range 100 to 300 hertz, which means that this signal, this sweep signal can be used to excite the structure over a frequency band of 100 to 300 hertz, right. So, outside this band also there is some signal energy present, but that is not significant. So, let us now use the sweep signal for shaker testing of the cantilever structure. So, we are going to use a measurement frequency range of 400 hertz and the record length is 4 seconds. So, now we generate a sweep signal with its frequency swept from 0 to 400 hertz in 4 seconds, and the amplitude of the signal is 5 volts. So, this figure shows signal generator voltage over a length of 4 seconds. Okay. So, the frequency of this voltage signal is 0 in the beginning, and then it increases linearly to 400 hertz at the end of 4 seconds. So, this signal generator voltage is now fed to the power amplifier, which then excites the structure using the shaker. So, let us look at the force applied on the structure and the acceleration at test point 5. So, on the left hand side what we see is the force on the structure, right, and 3 blocks of data are shown. So, let us focus our attention on the first block of data, which is 4 seconds long, and we observe that the force is fluctuating, is not it, and because when the frequency is swept from 0 to 400 hertz, it passes through the resonant frequencies of the structure, and we know that when the frequency coincides with the resonant frequency of the structure, there is force dropout. So, that is why we see that the force drops at certain instants of time. So, these are the times when the frequency is passing through the resonant frequencies of the structure. On the right hand side we see the response of the structure, and if we look at the first block of data, and we see that the response also undergoes a lot of fluctuation, and that happens because again as the frequency is swept from 0 to 400 hertz, it passes through the resonant frequencies and anti-resonant frequencies of the structure. So, when it passes through resonant frequencies, there is a large amount of response, and when it passes through anti-resonant frequencies, there is a small amount of response, and that is why the response also seem to be fluctuating a lot as the time progresses. So, here also we should now wait for the transient part of the response to die out, right, and the steady state to reach, right. So, once the steady state has reached, then the measurement should be taken, right. So, after spectrum averaging we obtained the FRF estimate and the coherence. So, let us look at the point inertance and coherence obtained in this manner. So, you can see the coherence is very good except at one of the resonant frequencies, right, and the FRF estimate is also very good. Let us look at what is multi-reference testing. So, up till now we looked at CISO and CMO measurements, right. These are basically single reference measurement. For example, we applied the excitation with the shaker at one point, right, and the response was measured at some other test point on the structure. So, we are applying one input on the structure and measuring response at one output, right, one test point. So, that constitutes a CISO measurement, single input single output measurement. If we use more than one accelerometer to take measurement simultaneously at more than one test points, then that would constitute CMO measurement. We are applying one excitation and then taking measurement at multiple test points. But these are all single reference measurements because we are applying only one input on the structure. In the Hammer test also we fixed the transducer at one location and took measurement of FRF by applying excitation at some point on the structure. That again is a CISO measurement, okay. But again there is only one reference because there is only one accelerometer used there, right. So, this CISO or CMO measurement gives us the one row or one column of the FRF matrix. So, there are situations where single reference testing may not be enough. One such situation is when we are interested to find the modes of the structure in the orthogonal direction. For example, if you have a beam structure, then the beam has modes in the vertical plane as well as the horizontal plane, right. So, by exciting the structure in the vertical plane, we can effectively find the modes in the vertical plane. But this excitation may not yield the modes in the horizontal plane because the modes in the horizontal plane may not be effectively coupled with the excitation in the vertical plane. Other situation is when there are symmetrical structures, right. Symmetrical structures have repeated roots. For example, if you have a square plate, then square plate will have pair of modes with identical natural frequencies but different mode shapes. So, such pair of modes also cannot be identified using single reference testing. Also testing of large structures like airplane, naval structures and machine tools also cannot be effectively done using single reference testing because with single input or single excitation point, the different parts of the structure cannot be sufficiently vibrated and the signal to noise ratio may not be good at different points, and therefore single reference testing may not help to identify accurate estimates of the FRFs and the model model. So, what is multi-reference testing? So, multi-reference testing involves FRF measurement with more than one references. For example, we can use more than one shaker for excitation. So, we can excite the structure at one point and we can also simultaneously excite the structure at some other point using another shaker, right. So, that constitutes multi-reference testing. So, this kind of testing will correspond to MIMO measurement, which is multi-input, multi-output measurement. So, we are applying excitation at more than one points on the structure and then we can take measurement at multiple points simultaneously. That would be a MIMO measurement. If we take measurement at only one point on, then it will be MISO measurement, right, multiple input, single output measurement. But then we will have to take several MISO measurements to obtain the all the desired FRFs. So, now the question is how FRF is estimated in multi-reference testing because we are now applying multiple inputs, but the FRF if we recall is defined for a single input. So, let us say there are now m number of inputs applied and there are n number of responses. So, now for m number of inputs we determine the matrix GFF, which is m by m, okay. So, it is the cross spectrum between every two inputs. Similarly, we determine the matrix GXF, which is of size n by m. which is the cross spectrum between every output and every input. Once these two are obtained, now we can obtain a least square estimate of the FRF, okay, which is given by this expression, which is H omega is equal to GXF omega and into inverse of GFF. So, in this way we obtain the FRF matrix of size n by m. So, this matrix has m number of columns, okay. So, we can see that in multi-reference testing now we get more than one column of the FRF matrix as opposed to single reference testing where only one column was obtained, okay. So, these now FRFs can be now processed using a poly-reference curve fitting method to obtain the model of the system. So, in this way today we looked at FRF measurement with a shaker using other random excitation signals, and in the process we looked at some variants of the random excitation signal, and we also looked at sine excitation. Now we stop here. Thank you.